Namaste everyone, welcome to my channel. As I've said earlier that I'll be making a series of revision videos of all the courses of Sudarshan Sir so that we can easily revise on the day before exam. So I'm going to not talk a lot in this video and immediately get on to the revision video. So let's get started. So in today's video, I'm going to be covering the revision of the interior of the earth and the earthquake waves and the evidences of the interior of the earth. So basically the starting of the lithosphere. Here I have covered the last bit of class 4, class 5 completely, and the 11th standard NCERT as well. So basically there was some factual points that sir had not covered in class and expected us to do it on our own, but I wanted to use this video exclusively for revision, so I have covered everything in this. So let's get started. So firstly we are going to cover lithosphere, and lithosphere basically comes from the word lith. Lith stands for rock, and rock is the basic structure of entire landform. And so we have to understand how the landforms. If we want to understand how the landforms are formed, we need to understand how the rock is formed. Rock comes from lava, and the lava comes from the magma, which is coming from the interior of the earth, which makes it very important to study the interior of the earth. And another thing that we need to remember is that nobody can actually reach down to the interior of the earth. So all of that we're studying today is going to be on assumptions, but there are certain scientific evidences and we are going to study the evidences as well. So let's get started. So there are earth is made up of several layers, the first one being the crust, then there is mantle, and then there is core. Core is further divided into the outer core and the inner core, and basically the crust covers some say 34 kilometers on an average, because in the ocean areas the crust is a little thinner, but in the mountain areas it is a little thicker. So on an average it is somewhere around 30 to 34 kilometers. Mantle is somewhere around till it is from zero is on the surface, and then when we go down, so till 34 kilometers is what is the crust. Then mantle is somewhere till 2900 kilometers, and then the core comes till 6371 kilometers as per the NCERT. So we need to remember that. Another thing that we need to remember is that what is the crust and core and mantle made up of. So crust is actually said to be made of two main elements, which is silica and aluminium, so that forms Sial, and that is mainly the continental crust. And then the oceanic crust is made of Sema, which is Sial and magnesium. Mantle is also made up of the same Sema. And the core generally is made of nickel and iron. So that forms Nephe. So Sial, Sema and Nephe, these are the three things that we need to remember. Also the fact that the core is extremely dense. So the density of core as per NCERT is somewhere around 13 gram per centimeter cube, and the average density of mantle is somewhere around 3.4 gram per centimeter cube, and that of the crust is less than 2.7 gram per centimeter cube. So these are the densities. It's a really average density. It is not the exact. Also, we need to remember that this density right here of the crust is actually said about the oceanic crust. The continental crust density would be lesser than this, but it has not been clearly mentioned in the NCERT, and so it is said that you shouldn't dig into it. So I think this is what we are going to cover. So how do we know this is what the earth is made up of? So in NCERT it says that there are several evidences. Some of the direct evidences include, firstly, if we want to go into the interior of the earth, first thing that we can do is dig, which is mining. So gold mines in South Africa are as deep as 3 to 4 kilometers. As we understood that the radius of the earth is some 6,371 kilometers. So this is really just a crack on top. It is really not much, but still it is something. So gold mines in South Africa, that's how we figured out how the interior works. Then we've also done some deep ocean drilling and integrated ocean drilling projects. The deepest drill has been conducted in the Arctic Ocean at Kola, and that drill is about 12 kilometers deep. And another evidence that we can find is also from the studies of the volcanic eruption, because volcanic eruption basically is something which is coming out directly from the interior of the earth, probably even more interior than all of these. So that's why this is really relevant. So these are some of the direct evidences. Then comes the indirect evidences, which includes meteors, because it is said that when the earth was formed, it was basically, meteor was also formed from the same material. So if we study the proper, if you make a proper study of the meteors, it could be similar to the composition of earth, which is how we can also find some evidences. There's also another indirect evidence in the name of gravity anomaly. Gravity anomaly basically stands for difference in the gravitational value. So gravity is a little different at different latitudes, because there is a difference in distance from core to the pole and core to the equator surface. So because the shape of the earth is geoid that we saw in the last video. So because of that, there is certain differences, and also the fact that there is a difference in density within the interior of the earth. That's why also there is a difference in the gravity. There's difference in the material. That's why also there's difference in the gravity, and this difference is called the gravity anomaly. Another indirect evidence includes the magnetic field. This again reflects to the difference in the material. So in core there is a lot of iron found, as we saw earlier, that nickel and iron are the main components of the Earth's core. So it forms a magnetic field, and there's certain difference in there. So that's how also we can figure out. And then there is seismic activity, which is the most important evidence, and we'll see how. Then first thing that we need to know is some facts. So lava is basically this is about the difference between lava and magma. Magma is basically when the rock is in the molten material in the interior of the earth. So till it is inside the earth, it is called magma. When it comes out in form of a volcanic eruption, it becomes lava. So lava is on the surface and magma is in the interior. Also, the fact that we need to know is from these evidences, like as we saw that lava is coming from the inside, which means that the interior of the earth might have high temperature. So when we talk about increasing temperature with increasing depth, the rate is 1 degree per 32 meters on an average. Another thing to note is that why is there such increase in temperature there? So Arthur Holmes in 1930, he conducted several studies on the lava, and he found out that radioactive elements are present in the interior of the earth, and these radioactive elements basically have their own thermal heat. And uranium is an example of one such radioactive element, and it is lighter. That's why it is found near the Earth's crust. But basically, these radioactive elements are the reason for increasing temperature with increasing depth. Marking the important elements in the Earth's crust and the entire Earth in its descending order of its availability. So the most important thing to remember is that on the Earth's crust, as such, when we say Sial and Sima, we all think that silica will be the element, but it is not. On the Earth's crust, oxygen is available in the most abundant, and then comes silica. So 47% and 28%. As such, I don't think we need to remember the exact numbers, but still, first is oxygen, then is silicon, and then there's aluminium, and then there is iron, and then there is magnesium. So these five, I think, order of these five is what I think we need to remember. And for the entire Earth also, we'll remember the top five. The first one here is iron, because iron is available in abundance in the core. So when we look at the entire Earth, iron is available the most. Then second comes the oxygen in form of oxides, then there's silica, then there's magnesium, and then finally there's nickel. So aluminium is very less when it comes to the entire Earth. It's mainly there only in the crust area. So that's how the distribution of the elements is. Then we move to the structure of the Earth. So in structure, as we've said that the topmost layer is the right here is the crust. On the crust there is oceans as well as there is the continent. So here is the continent and right here is the ocean. So as we can see right here, the crust in the ocean area is quite thin, whereas in the continent area it's quite thick. So basically, the crust goes up to some 34 or 35 kilometers. Right here, see, 32 kilometers is what it says in this figure, but in NCERT it says somewhere around 30 to 35. So I think we are going to remember that. Then the next layer is basically it comes in mantle, but as we've seen that the temperature decreases with increases with increasing depth. What happens is, as we go below the 34 kilometers and even below that, when we reach the mantle, some up to some 100 to 200 kilometers of depth. This depth varies in different regions, so 100 to 200 is the average. That's where we find that the temperature is too high, but also the fact that the pressure is too high as well. So because of high temperature, the rocks over there would want to turn into liquid, but since the pressure is high, they can't completely turn into the liquid form, which is why the layer over here is semi-solid, and semi-solid layer is called the asthenosphere. It is partially molten, and astheno means weak, which is why it is called a little weak layer. So it is a semi-solid layer, and this is basically what is the magma chamber. And from here is where the volcanic eruptions occur. So because of the fact that lithospheric slab might crack a little bit, the pressure will be released in that much of area, and the magma will come out, and that's why it will get a chance to turn into liquid, and again that's why we have volcanic eruptions. So basically this is the asthenosphere. The asthenosphere is basically the semi-solid region of the mantle. So the uppermost region of the mantle is still solid, an entire solid region. So the rigid crust and the upper mantle forms the lithosphere. So there is lithospheres up to some 100 kilometers, 100 to 200 in some areas, and then from there up till 700 kilometers is the asthenosphere, which is a little semi-solid region. And then from there to lower mantle, the pressure becomes extremely high. So that's why because it's up 700 kilometers worth of material on top of that area, which is why even though the temperature is high, it's not going to get chance to be semi-solid like the asthenosphere, which is why this area is rigid, and this is called the lower mantle. This area is also called mesosphere because since we have different names for all the different layers, as in when its density and its state changes. So first rigid layer is lithosphere, then comes asthenosphere, and this lower mantle region is called mesosphere. Then after mantle comes the core. The core also has two different layers. So now first thing that we need to remember is that core is made up of nickel and iron, and it is very different from the SEMA that we had above. Silica has very high melting point, so it takes a very high temperature for it to melt. But the core is made up of nickel and iron is in the most abundance here. 80% of the core is formed with iron, and iron basically melts at much lower temperature. So even though the pressure is extremely high, but the temperature is so low that the temperature is so high as well that it dominates here. And since iron has very low melting point as compared to silica, this part of the core, the outer core rather, is going to be in the liquid state, and the inner core has the most pressure of from all the sides, which is why the inner core is going to be extremely rigid. So even though it is made up of nickel and iron, but still the inner core is going to be rigid and the outer core is going to be liquid. Also, what we need to know is that the core region is actually called barysphere. So outer core is outer barysphere and the inner core is inner barysphere, but it is still barysphere nonetheless. Now, the asthenosphere was up to 700 kilometers. The lower mantle, on the other hand, goes on till 2,885 kilometers here. In the NCERT, it says somewhere around 2,900 kilometers. And then the outer core goes on till 5,155 kilometers, and the inner core goes on till 6,371 kilometers. One thing that we need to certainly remember is asthenosphere does not start directly from the upper mantle. Some part of the upper mantle also goes in lithosphere, and not even complete upper mantle goes in lithosphere, only some part of upper mantle goes in lithosphere. Now, how do we know about all of these different layers? We know this mainly because of these evidences that we talked about earlier, but one of the main evidence is the seismic activity. For that, we need to study the earthquakes. So let's get on to that. So earthquake basically are of different types. One is, there are some natural earthquakes and there are some man-made earthquakes. Natural earthquakes are mainly of two kinds, one of them being the tectonic earthquake, and another one is the volcanic earthquake. Volcanic earthquake is when there is a volcanic eruption. As we already observed that because there is a crack in the lithosphere, the volcanic eruption happens, and because of that there might be certain movements in the lithospheric slab, which will release certain energy, and which is why there might be vibration, and that's how earthquake is generated. So that is one earthquake that we already talked about a little bit earlier. The tectonic earthquake is when there is movement in the lithospheric slab, but not necessarily there is a volcanic eruption. So that also releases certain energy, which generates some vibration. Another type of earthquake is a man-made earthquake. Man-made earthquake include the collapse earthquakes. This is when we go mining very deep and without considering the pressure, or without considering the nature. Basically, when we keep mining without the safety measures, there's a chance that certain part might collapse, and that might also release some energy and cause earthquakes. So this happens due to mining. Then there is explosion earthquakes, when there is a nuclear explosion or explosion of a great, some missile or something. That's also when earthquake can happen. And then there is reservoir induced earthquake. So when we construct dams which are of like really high pressure, and again we do not take into consideration the capacity of the rock or the capacity of the nature, that's when this kind of earthquake can also occur. So these are the different types of earthquakes. Now exactly how the earthquakes happen. So what happens is there's a lithospheric slab, and because of the movement on the asthenosphere, because it is a semi-solid layer, the lithospheric slab is basically of a little lesser density than the asthenosphere, which is why it is floating on top of the asthenosphere, and it might move, and basically the slab in the bottom might get displaced, or even in the middle, basically because of the movement. So some rocks in the lithospheric slab can get displaced. Because of such a displacement, there might be some energy that is released. Now where the displacement occurs, that is basically the point where the earthquake is starting. So such a point is basically called focus or hypocenter, and then from there the energy is released, and it travels basically in all the areas. But the nearest point is going to be when it goes to the surface, the nearest point on the surface of this epicenter is going to be perpendicular, and this nearest point is actually called the epicenter. So hypocenter is inside in the interior of the earth, and epicenter is on the surface of the earth. From the hypocenter, the energy reaches the epicenter in form of waves, and these waves are called the body waves, and from the epicenter it basically spreads throughout the surface, again in form of waves, which are called the surface waves. On surface, basically there is a seismograph which marks the amplitude of these waves. So the seismograph looks a little bit like this, and as you can see that it basically marks the amplitude of the waves when the earth moves. It basically marks this kind of a graph, and this graph measures the intensity of the earthquake. Now this does not have a numeric value. In order to get a numeric value, we use Richter's scale, and this actually measures the amplitude, actually measures the magnitude of the earthquake. The Richter scale. And the Richter scale it measures the magnitude from 1 to 9, and it is believed that above 6, if the magnitude of the earthquake is above 6, then it is considered to be a little disastrous. Below 6 is not that damaging. So above 6 is really damaging. Earlier, we used to measure this instead of Richter scale, we used to have Mercalli scale. So now we don't use it, so it's not that important. But if at all it comes it appears in some sort of multiple choice questions, we need to remember that Mercalli scale is associated with earthquake. Now, as I mentioned earlier, that the earthquake basically travels in form of waves, the energy released in form of waves, and there are two types of earthquake waves. One is body wave and another one is the surface wave. So there are two types of body waves as well. The first one is the P wave or the primary wave, and the second one is the secondary wave, which is the S wave. So P wave travels longitudinally. So if we can see right here in the diagram, it basically goes like this, like a sling that we used to have, spring basically. It is basically similar to the sound waves or the pressure waves, and it creates difference in the density because it stretches and then it compresses. So that's how it moves and that's how it propagates, and it creates this kind of damage if it does at all. The second type of wave is the secondary wave, which travels transversely. It is basically propagating transversely, so it basically goes perpendicular. If you see right here, it creates such perpendicular up and down motion. It looks like a water ripple, and it also travels like light. These are the similarities. S waves travel a little slower than the P waves, and these are really faster. Another thing to remember is that P wave can travel through solid, liquid as well as gas, and S wave cannot travel through liquid or gas, it can only travel through solid. So these are some of the differences that we need to remember. Also, we need to remember that these are waves, so basically they are going to change their direction and their speed with change in medium. So how we can understand the interior of the earth using these waves? So when the earthquake is initiated, when it is at the hypocenter, from there, suppose this is the hypocenter of the earthquake, from here it goes to the epicenter, and from there the propagation is different, that is surface wave. But when it is still inside, it basically goes into all the directions. So what we had observed is seismographs were placed, at the places, various places on the earth where there is high probability of earthquakes, and it was found out that if the earthquake starts here, S waves basically do not go in straight line, they kind of deviate, which indicates that there is difference in the medium, and the entire earth is not homogeneous from the inside, and there's difference in density. So it was found like that, and it was found that it goes from all the way, it reaches all the way till here, but when it hits the core, it does not go through from core, and it basically is not detected in this area. So this is the area which is called the shadow zone for the S wave. It does not go through there because, as we understood earlier, that S wave cannot travel through liquid or the gas medium, and we figured out that the outer core is in the liquid medium, and which is why it couldn't travel. So this is how we could prove that the outer core is of a rarer medium. So it could be either liquid or gas, but there's a more probability of it being liquid than gas because of the pressure. So that's how we figured out about the outer core being liquid. Another thing that we realized, why is inner core solid? We figured it out by the shadow zones of the P wave. So if there is this is the hypocenter, we found out that P waves can go through the entire, it can travel through all the mediums, but as we said that it basically refracts when there is a change in medium. So on the outer core, we found out that since it is liquid, it changed its direction, and again in the inner core also, since it was solid, it again changed its direction, and again then it changed its direction while reaching from inner core to outer core, and then from outer core to the mantle area, it again changed its direction. So basically there was a lot of refraction, and which is why this part is considered to be the shadow zone of the P wave, because it didn't reach this part. Even though it went through the entire earth, it couldn't reach in these parts of the earth if this was the hypocenter. So the shadow zone of P waves is from 103 degrees to 142 degrees, whereas the shadow zone for S wave is from 103 degree to 103 degree. This entire part is the shadow zone of S wave. So we have been able to figure out that the shadow zone of S wave is much larger than that of the shadow zone of P wave, which is only this much and this much on both sides. Another thing that the scientists were able to conclude was that the P waves basically travel fastest in the most dense mediums. Basically, if it is solid, it can travel the fastest. So it was found out that the maximum speed of P waves was detected in the inner core, which meant that it is extremely dense. So this was how we were able to find out the different layers and their state in the interior of the earth. Accordingly, to kind of distinguish in different layers, now various scientists have conducted some experiments, and they have figured out some discontinuities, that from this particular point it refracts, and so accordingly they have the scientist who has basically figured out a certain discontinuity, they have named that discontinuity with their with reference to their own name. And so these are the different discontinuities that we need to remember. The first one that we need to remember is between the lower and the upper crust. So as such, the upper and the lower crust is still the part of crust, and there is not a lot of difference, but still there is difference in density, because the upper crust might have a lot of continental it might have continental crust which might be a little less dense, and then there's Sima, which is a little more dense, which is the oceanic crust. So basically, to mark that density difference, the first discontinuity is the Conrod discontinuity. Then we need to remember the discontinuity between the lower crust and the upper mantle. So as such, it tries to show the discontinuity between the semi-solid and the solid, so the asthenosphere and the lithosphere. But it is still said that it is not exactly after lithosphere. It is said that it is in the between the lower crust and the upper mantle. But we need to remember that some part of the upper mantle is also included in lithosphere. But even so, if either is asked, we need to mark that this is the Moho discontinuity, Mohorvik, or simply we can just call it Moho discontinuity. Then the next discontinuity that we remember is between the upper mantle and the lower mantle. Now there also there is a very distinct difference, because the upper mantle is going to be the asthenosphere, so it is going to be the semi-solid state, and the lower mantle is rather rigid. So to kind of mark that discontinuity, it is called Repeti discontinuity. So right here is the Repeti discontinuity. Then comes the Gutenberg discontinuity. This discontinuity is basically marking the distinction from the upper core or the outer core and the lower mantle. So the outer core is again liquid, because there the iron is found, and it has low melting point, as we discussed earlier. So it is going to be in the liquid form, and the upper and the lower mantle is going to be in the rigid form. So that discontinuity is the Gutenberg discontinuity. And then the outer core is liquid and the inner core is extremely dense and it is solid. So that discontinuity is marked by the Lehman discontinuity. So this can be basically remembered with the basic, a short abbreviation CMRGL. CMRGL. If we kind of say it a couple of times, we will be able to remember all the discontinuity in its order. So C stands for Comrod, then there is Moho, and there's Repeti, Gutenberg, and Lehman. Then we move on to the surface wave. Surface wave are basically of two types, Rayleigh wave and Love wave. They are not really mentioned in NCERT, the names of Rayleigh waves and Love waves, so it's really not that important to remember. But I actually did put the image of Love wave right here, so that we can just say that love is the most destructive one, because surface waves are considered to be the most destructive waves. They travel on the surface and they basically go again in the transverse manner, just like the S wave. They propagate in that manner, and they are the most destructive ones. Also, what we need to remember is that in terms of speed, P waves has the highest speed, and then comes the S waves, and then comes the Love wave. I'm writing here because S waves will, if I write S for surface, then it will be a confusion. So this is of the highest speed, whereas when it comes in terms of destruction, it is exactly the opposite, where L wave causes the most destruction, then comes the S waves, and then comes the P waves. Last point that we need to remember about the surface wave or the L wave, the Love wave, is that it can travel through a solid and the liquid medium, but not the gas. Liquid medium we have already seen, because it is what causes tsunamis, and in the solid medium it causes the earthquakes, but it does not travel through the gaseous medium. So that was my video for today, guys. I hope you found it useful. Do use it and watch it in 2x just before the exam, and it will sort out your entire chapter of interior of the earth. You will not need to, because I have covered the NCRT as well as Sudarshan Sir's video, and I think it should be really helpful for you. If you did find it helpful, please leave a thumbs up because it really encourages me, and do comment and let me know if you want me to keep making such videos. As such, I am going to make these videos because it's going to be useful for me as well. Any which ways, thank you so much for watching this video. And if you have not subscribed to my channel, please subscribe.